Okay, so to get things started in this meeting, I have this notebook here is just like an outline with some very high level notes, like doing a very fast overview of some of the methods we had covered in the book. But the reason I want to do this is because for the first part of this session, um, we I wanted to look at like the first part of these techniques in the book that we looked at, which involves these tabular methods and some exact solution methods, and then compare that to a sort of a search approach to the problem. And in the last meeting we looked at the Rubik's cube problem, which is very large in terms of the state space. Like it's way too big, like to store in a computer, for example. But a very similar problem we can look at. Even in the last session, I showed how you can pare the problem down and shrink the state space by looking at a smaller set of solutions that are closer to the solved state. And we can also look at an even simpler problem, which is sure people familiar with the Rubik's cube might also be familiar with a smaller version of the cube where there's only two or four. Like instead of it being 3 by 3, it's just a 2 by 2 cube, and that cube's actually plenty small to fit in a computer, and it's what we can at least compare some stuff. And sometimes when you're looking at more complicated methods, it's useful to start with a problem where you actually like already know what the answer is to see what it takes, how your other solution method is scaling with that. So look at that, and then if we have some time, we'll see. We can talk about some other problems or go in other directions if people are interested in. So for all the reinforcement learning methods, as someone had already mentioned, they are all Markov decision processes, and the solution techniques that we use exploit that property of the system, and they exploit the Markov property. In order to do that, we're really usually interested in the state information of the problem. So, whatever problem we have, there is a specific state space that we can look at, and we know in particular, which state we're in. And then if we know about the system, we also know what the transitions look like from that state to other states in the system. And it's, exploiting that information about how the states are connected is why a lot of these techniques have really efficient solution methods compared to other methods like some of the more exhaustive search methods that I'll talk about later. So when we have these Markov systems and we have, if we have a lot of all the information we want to about the problem, our goal is to use these techniques to get, a single global solution to the problem where we actually know what is optimal to do at every state. And we're like simultaneously solving for that solution for every state. And of course, like this requires computing a lot of stuff ahead of time, whether that's sampling from the environment or analyzing the environment, like the information we have about it. And it's really like you'll see it down here, but everything's abbreviated here, but this P function, this represents the probability transition function, which tells you the probability of all of the state transitions in the environment. And really, this alone is like all of the information that we need to solve the problem. And then, when we don't have this function, like maybe we only have access to like a black box version of this, then we have to rely on, sampling techniques, and we can't really guarantee to get an exact solution, but we can get sort of arbitrarily close to one if we spend enough time, training it, collecting data. So, when we talk about, solving one of these problems, there's this objective that we define, which is this discounted sum of rewards. We could also think about the average reward for other types of problems. But the first thing we're introduced to is the discounted sum of rewards. And this is just, whenever we have these transitions, there's some reward value associated with it. And this is, to be very generic, we could just get rewards on every step. It could be, this function could be anything. But if we have a simple, like, if you think about like this problem or like a problem with a maze or like something, oftentimes a lot of these problems are like goal problems where there is one or more goal states that we're trying to reach. And we're trying to figure out, how to get to the goal state as quickly as possible. And for those problems, like the reward function is quite simple. Like it's either going to be just a positive reward for the goal state, or maybe like a penalty if it's like a negative goal that we're trying to avoid. And, in that case, like this sum, it really only matters like the last value of it or something. Or all the rewards could be a -1 as well in a problem where like that's another way of designing the problem so that we're incentivized to reach the goal as quickly as possible, because it's sort of a way to find the solution in the fewest number of steps. And for that type of problem, we can compare these techniques pretty directly to sort of like pathfinding algorithm, because those algorithms are designed to find a path to a goal. Of course, not all RL problems are these goal problems. Like it could be something totally different than that. There could be all kinds of reward values that occur in different types of state transitions. So this is definitely more flexible as a framework than something like just a pathfinding algorithm. But if we have a problem like that, we can compare the two. So we're trying, like, we have to design our problem so that there's some reward which indicates what is important for us in terms of behavior, such that if we find a certain behavior that gives a higher sum of reward, so we could expect on average to accumulate more reward, then we can use these techniques to find a way of doing that. And the first way that we think about, and this is like all the exact solution methods follow this framework, is to use these value functions. So a lot of the time we spend is on all the techniques to actually compute the value functions. And like the value functions are directly tied to this G value. They're actually like, they are supposed to, if they're computing the right thing, they're supposed to compute the expected value of this from a particular state that we're in. And we had, two kinds of this. There was the state value function, where we care about this expected value starting from a particular state. Following this little pi is for the policy. So the policy is what controls the behavior in the environment. And given a policy, we can then compute this value function, which tells us how well does the policy do in terms of accumulating reward from every state. And there's also the state action value function, where the only difference here is that we set a particular action that is taken from that state, which is independent of the policy. So we have both of these, and the reason why we need both of these is because there are situations where we can get away with only using this, and there are situations where we also need this function as well. So what's being shown down here, this first part is just the definition, the value function. And then this is something which we had derived, which is the Bellman equation for this, which is a recursive relationship for this function. So we had derived these equations as a way of, of computing this. We can basically compute this by doing a fixed point iteration with this operator, right? Because these two things will be equal when the value function is correct. And those were the approaches we took to compute these value functions. And then, after looking at the value function for a particular policy, then where we actually got into calculating optimal behavior for these systems was looking at what are the properties that the optimal value function would have, and then how do we actually find the optimal value function? And this is where we had, the optimal value function has this special property where, first we made a very vague statement, which is we would like to find a value function such that its state values are higher than the state values of any policy, like in the entire policy space. And it sounds like something which is impossible to figure out because the policy space is, a huge space. It's like, entire space of all possible behavior that you could take in an environment. But we were able to find a much simpler thing to evaluate, which is that if we find the optimal value function, either for v or q, it it has this property. And again, this is another recursive equation. These are like the Bellman optimality equations. And again, the nice thing about this is that it reduces this impossible task of searching the entire policy space into a much simpler task of just like doing a fixed point iteration with this operator, right? And we can do it either for v or for q. It looks very similar to this. The only difference is here, the policy is gone. It's replaced with this maximization function. And then, on top of this, we then introduce the idea of policy improvement, which we don't actually like always need to think about policy improvement, because I just mentioned one way of calculating the optimal value function is to just look directly at these equations. And we can actually use these directly to find it. The other way that we can use, and this becomes important when we look at other techniques, is the idea of policy improvement. And for policy improvement, the idea is that we start with one policy. And then if we find a second policy that has this property, and this property is that if we look at the value function of the original policy, but we replace the action with the action under the new policy, and we get a larger value. So like that means that taking this action is preferable in this state, more preferable than taking the action for the original policy. That actually, we were able to prove the policy improvement theorem that this meant that this new policy is actually better in general. Like it has a better value at every state just from knowing this fact about it. And the nice thing about this fact is that it's really easy to construct this policy pi prime. All we have to do is look at this q function from our original policy. And then if we construct this, the argmax of it everywhere, then it already has this property just by construction. Now, there was already this relationship between, or you can derive these relationships between v and q, and actually what's being shown here is that even though, this looks like you need the state action value function to calculate this, we can actually get away with only using the state value function as long as we have this information here, right? This information being that probability transition function. So like the point is, if we don't have this information, we can still, construct this better policy without this, as long as we have this function as well, or some estimate of this function. And then if we have this information, then we can get away with only worrying about the state value function, which could be, useful because this is a simpler function, right? It's only a function of one argument instead of two. So, this construction is called, the greedy policy with respect to the value function. And then if we keep doing this, and there's some point where this policy that we try to change, like, right, we have like pi and pi prime. If we have a situation where after doing this change, we still have the same policy, then we also know that we've arrived at the optimal policy and value function. So, and this is, a different approach to getting the optimal policy. But this also works. And sort of, using this approach compared to this is more like when we did value iteration. Like value iteration is when you directly use this optimality equation. And then policy iteration is when you repeatedly do these steps of policy improvement. So, this is like, these are all like exact functions here that I've written out. But so these exact functions are what we solve for when we do like the very first techniques that we looked at in the book. And like the first section of the book covers tabular methods. Now, tabular methods are just methods where we can explicitly like have a list of all of the states and also all of the state values that we need, which also means that we can represent our value function as just this list of values, right? Like this function, like if all these s's are some finite, things, we could just index them. And then, both of these value functions that we're interested in can just be a list of values. Or, in the case of Q, it might be easier represented as a matrix of values because we have two different indices. But that is what we did with tabular methods. And when we use these methods, we try to, we build a value function as just this list. And then we either learn the optimal value function directly, like we do in value iteration, or we use the policy improvement process where we keep constructing this argmax policy. So for the exact solution methods, like policy iteration or value iteration, this requires that we have this complete knowledge of the environment, which is this probability transition function. And then I already mentioned this, but yeah, when we use value iteration, we do this fixed point iteration on the optimality equation I showed earlier. And then with policy iteration, we have this sequence that we construct where, right, we have like pi and pi prime, and then we keep just making new versions of pi and then new value functions associated with it. And each time we do this, we should get an improved value function. And here, like the meaning of an improved value function is very clear. Like it will actually have a better value, a better or equal value at every single state. So there's like no compromise. It's just strictly better than the old one. And then in both cases, when we stop improving or like this iterative process stops producing any change or change within a threshold, then we know that we have stopped and reached our optimal value. So yeah, and of course for all the exact solution methods, since we do have this probability function, I already said it is sufficient to stick with the state value function, right? We don't need to worry about anything else because we can always construct the action value function with this formula, right? Where we sort of, this is like a one-step look ahead at all the possible transitions, which of course we can only do if we actually know what all of those possible transitions are. Yeah, okay, so that is sort of it for the theory of the exact solution methods. I can show some examples from the other notebooks of how this working in action, but are there any questions so far about the theory of this? I know if you haven't looked at this before, it's not going to make that much sense because I'm skipping all of the proofs and everything, but I'm just trying to, yeah, to lay the groundwork to get to the next part. Okay. Okay, so I will assume this is good for now. Okay, so let's look. So this is just showing this actually working in one, like a very simple toy example problem for this. But so this is like a grid world environment here. I'm just going to take this back. So what this is showing here is like a typical like way you would use policy improvement, which is here like you start with a random policy. That's what's being shown here. This is like a grid world where there's a starting state and then a couple goal states. And this is also, yeah, this is the discount rate. So yeah, this is like framed as a discounted reward problem. And then this is the value function that is associated with this random policy. And then when you do policy improvement on this, we advance this. What's being shown here, so this is the greedy policy with respect to the previous value function that we had. And then this is the new value function. And every step of this, we take this new value function and we get the greedy policy with that. And now it's a little better. And then each time, basically, we just have a strictly better set of values. And you can see like here, the optimal policy is very simple. We just go straight to the goal with this slightly added complication that actually this goal has a different value. So there are states where if we're close enough to this goal, it is preferable to go here. But this boundary actually depends on the discount rate. And it also changes if we make this a continuing task. So this is like done as a discounted task. If I make this a continuing task where it doesn't end, like it just keeps resetting here, and we're in that case, the objective we're interested in is the average reward rather than this discounted reward. Where here, like this causes the rewards to exponentially decay into the future. It creates a particular relationship between like the present values and the future values, right? Like they're not like decaying linearly or anything. It's yeah. Whereas if we do the average reward, it's sort of it it ends up being a just fundamentally different solution because of that. But here, like in the average reward, you can see that now there's a different boundary of where it's preferable to go to this goal because of that. Yeah, because it's just not the same objective. So this is something we had talked about going over this part of the book where this discount rate and how you design the rewards actually will affect the solution to your problem. And I mean, this is a very simple problem. Like it's easy to just see what's happening here, but you could imagine this is an abstract representation of something much more complicated. And if you do have different goal states with different reward values associated with them, like which one you go to is not, it's not very simple because it depends on this like distribution of all the different numbers of steps it would take to reach that other goal. And sometimes like what you actually want in the problem could be more of an average, and sometimes it could actually be where this discounting matters. But oftentimes the purpose of the discount rate is just to make the problem solvable, to make the values finite. And like the fact that the solution changes, here I can change this here to like 0.2. Like the fact that the solution changes as I change the discount rate, is not that desirable because it means that we actually need to have like an idea of what to set that value at, and understand what it means in the context of our problem. So yeah, it could be an issue. So this is showing policy iteration. For value iteration, this different, right? We don't have this like sequence of policies. We just directly solve for the value. So that's what's being shown here is that this this shows like 12 iterations. So this is like how many times we had to go through the state space to find the solution, where like when you do value iteration, you're sweeping through the entire state space and doing that Bellman optimality update. Okay, so yeah, this is showing just a simple, this like simple grid world environment. So what I want to do now was return to that, the Rubik's cube problem, or in this case, that the simpler version, the pocket cube problem, and show what the exact solution method looks like on that. So let me see. I have this. Okay. Okay, so let's see. I don't think I showed this before. I think I only showed the larger cube, but this operates in the same way. Right? It's just like you could see that all the sides of the cube, it's only 2 by 2, but the moves are the same. And actually, for doing value iteration, it turns out because this cube is simpler, we actually only need to worry about rotating like the first 3 faces. It's redundant to also consider rotations of the others because you can just reposition the cube and get the same state back. I mean, the other way of saying it is like you don't have to worry about rotating faces opposite each other because like rotating one face and then like if you rotated the opposite face, you could always get that state by rotating the front face and then rotating the entire cube. So yeah, this is not true of the full Rubik's cube though. For that, you can't ignore like you opposite faces because they're not always independent of each other like that. So here like again, I'm just representing the cube with all of the different faces. So here there's 6 faces, and then there's 4 of these like facelets on every face. So there's 24 of these, and here we can just index them from 1 to 24. And this is just I'm just imposing some ordering on the cube where I'm just counting like 1, 2, 3, 4, 5, 6, 7, 8. I have a face order and then an order in which I count the cubes on every face. And then this represents the vector of like what the solved cube is. So like when the cube is solved, all of these, like here I'm showing the colors, but the colors don't actually matter. Like what matters is each of these bases is a distinct piece. And you can see that like on a full Rubik's cube where even though like both of these squares, are green, like this green square has different pieces that are to the like, well, this is like an edge. Sorry, this is a corner piece, and this green corner piece is totally different because it has different faces on the opposing corners. So even though there are colors, you can think of every piece as distinct. Of course, when you're rendering the cube, it's helpful to render it with colors, but really, I'm just going to think about it in terms of this list of indices, and then for sort of the fastest exact solution you can do. It's helpful if you reduce the action space. Somewhat in this problem, it doesn't matter too much because it's a pretty small problem. But here, these are the 3 moves that I'm considering. So I'm just considering moves of the front, top, and right faces, right? These are all like non-opposite faces. So rotations of each of these interact with the other 2. So it's 3 moves here, and then here's an index of moves, and then sorry, this is just defining how each move permutes the indices of the cube. The idea here is once I have this, I'm also going to create a lookup table of these rotations so that I don't have to actually compute it each time, because I'm going to be repeatedly doing this. So it's helpful to just know for any one of these 3 moves that I do, how does that transform the indices of the cube? Which is just this lookup here, right? So this is showing, right, 24 indices. And this is showing basically how all those 24 indices are mapped when you take, any one of these 3 moves, right? So now it's very now easy to apply one of these moves. We just re-index the cube with these lookup indices. So, to apply one of these exact solution methods, we have to enumerate all of the states in the problem, right? So I have this rotation function here where I'm just rotating it. The reason why these are all, if you're curious, these are all just static vectors because, I know these are all of length 24, and I'm also using only 8-bit ints in the indices here, right? Because this is the smallest, native integer data type available. And right, I actually don't even need 8 bits here, but I'm just using it for convenience because the highest value is 24. So I don't need I certainly don't need more than 8 bits to represent that. So we have to build the list of states. And this, could be a somewhat cumbersome process. Here, what I'm doing here is I'm just maintaining a set of all the states, and then I'm applying all of the possible rotations to the state. So I have like 2 lists actually. Like I have a set of states for which I haven't tested all the rotation moves. And then I have a set of states for which I have, you know, explored and unexplored. And the idea is that as I generate new states, I'm putting them in a set, so redundant states are not copied. And then if I explore, all the states, and I don't produce any state which is outside of the explored list, then I know that I'm done. I'm done, constructing the entire state list. And if you tried to do this for the Rubik's Cube, it wouldn't work because you would just run out of memory and it would take forever and you wouldn't have enough space anyway. But in this case, we can do this and see how large the state space is. So, for this problem, do this, and this is just a list of all of these states. And we can see that it's only 3.67 million states here. So, not too bad. It only had to do 21 rounds of these of going through and exploring all of the unexplored states and generating new unexplored states. And so it only took about 21 seconds. Also, I wrote this in a way where it doesn't. It sort of keeps a data structure of the state that I'm transforming, so that I don't have to keep. So this actually isn't even running in parallel at all. This is just going in a sequence and it keeps adding to the set one at a time. So even just doing this one at a time without any parallelism still only took 21.8 seconds. But that's some amount of time. But the advantage of doing this is that we'll see that once I have this, I'll be able to get a global solution. And the question is then, is that worth it? Is this construction and pre-processing actually worth it compared to some other technique where we wouldn't have to go through this this exhaustive process of looking at all the states. So here, this is a function that actually builds the MDP that I'm going to use. And so for this I'm building a tabular problem, as I said. In order to define, this is like in the code I've written, but in order to define one of these tabular MDPs, you have to provide the state list, the action list, right? So in this case, I'm only using the 3 moves that I mentioned to make it, take as little memory as possible. And then the transition function, which for this is a deterministic problem, right? So every time you make a move, you know exactly what the transformation is. There's no randomness to it. There's only one transition state. So for this type of deterministic transition, I only need to define these 2 things. So the state transition map is just a matrix, which is a mapping for all of the state action pairs to the index of the state that it becomes when you apply that action to that state. And here, because this is a tabular problem, all the states and actions are represented by their index in the list, right? Because we don't actually need to worry about what the state looks like. We just need to represent it with its index. So inside of here, I'm just applying all the rotations and then getting the mapping it to the appropriate state. And then the reward transition map is just the same kind of matrix, but it just has the reward value for that transition. And I'm also constructing this as an episodic problem. So there is a terminal state. So here I'm defining like the terminal state is also like a look. It's actually a bit vector in this case. or sorry, oh wait, I don't actually, okay, yeah. The thing that tells you if the state is terminal or not will end up being a bit vector, which just indicates whether each state in the state list is terminal or not. Here, there's only one terminal state. The property of the terminal state is that there is no way to transition out of it. So that's why what's being shown here is just for the part of the transition function that represents the terminal state, it just stays in that state and all the rewards are 0. So that is like what makes it a terminal state. And then for every other transition, the reward is -1. So this will create a problem where when we're done, our value function should represent negative the number of steps it takes to reach a solution. And so that way, this can be an undiscounted problem where, if something is 5 steps away from the solved state, it should have a state value of -5. So it should be very easy to interpret the values. Yeah, okay. So here, yeah, so this builds the MDP. Building this, of course, is easy once we have the state list, but if we don't have it, then we do have to construct the state list. So here, this is building the MDP. Most of the time is probably just spent allocating all of the memory for these transition functions. But then here's what it looks like. Yeah, so we have here, this is like the bit vector terminal state. So all these are false except for the single terminal state. Okay, so we construct the MDP, and then here, once we have the MDP, we can apply the value iteration algorithm, which I showed before on the grid world problem. And here, we get the solution. So what's in the solution? So first of all, we have the value function. So here, this is a value function. Obviously, it's condensing a lot of it, but because it has a value for all of the 3.67 million states. And this is really what we care about. Yeah, the value function. Now we also have the optimal policy. Now, normally this is a deterministic policy when you do this because you're taking the argmax. However, if we have equal, it's possible that the state action values for 2 different actions are equal to each other, right? In which case, the argmax, we could just choose one of them arbitrarily. The way I have chosen to go about this is that if the values are in fact equal, then the optimal policy represents that by assigning equal probability to all of the actions. So we can see, for some of these states, like in this particular state, there's a single deterministic action, which is best. But in some of the other states, like in this one, all 3 actions are equally good with, that's why there's a 1/3 probability here. And, here there's 2 equally good actions. And we can also see how many iterations. So this took 20 iterations to compute this value function. Okay, so then, we have this optimal policy. So what this is showing here is now, sorry, so this is showing running, this is running an episode, using this optimal policy. So here it took 15 steps. This is a list of the actions that we're taking here. And then, this, because the way we designed this problem, we get a reward of -1, per step. And then these are all of the cubes that we end up with. And I think, sorry, so I didn't actually, here, let me see if I can actually display these. Actually, I think I'm going to have to. Okay, let me see if this works. Sorry, I have other examples where I'm actually displaying what this looks like. Okay, yeah, good. So here we can see here the actual final state is not shown here. This is actually the index of the final state, which is just the solved cube. But here, it just starts with a random one from the state list. So this is the starting cube, and then this is the sequence of all the cubes along the way of being solved. And you can see here that this is just one rotation away from being solved, right? Because these two will be corrected here. So yeah, also the way I design this, so normally when you look at these cubes, a more common, like this extrema, right? So this is like the solved cube is solved, it's 0 moves away from solution. And then the cube farthest from solution is 19 moves away. But remember, this 19 is for the set of moves that I'm using here, which is just these 3 moves, right? Like I'm only using 3 moves so that all the transition functions, only have to store 3 actions. It's more common for these problems to not just consider, like, if you rotate a face like clockwise, right? You can get to all the other positions of that face by just repeating that rotation up to like 1, 2, or 3 times, right? And doing it 3 times will be equivalent to going counterclockwise. But when people talk about like how many moves it takes to solve, they usually mean assuming that a single move could be either clockwise, counterclockwise, or a double move where you take a face and put it and rotate it, completely 180 degrees. So if you use that metric for the moves, then you end up having fewer moves that are required for a solution. And actually, I have a different version of the problem where I also use that metric instead. Actually, let me see where that is. It's down. Or actually, maybe see, where is it? Oh yeah, here. Okay. So here I have now a second version of the MDP where now you can see now there are 9 moves, right? Because before I had just the 3. So basically I'm multiplying the set of actions by 3 because now I'm considering not just the clockwise rotation, but also the counterclockwise and the double rotation for each face. So we triple the number of values that we have to store, but we end up getting a solution that would match more closely what would be seen when you compare this to other solutions in literature. So let's see. So this took. So here we can see actually when we look at the extrema, now we have -11 to 0, and this is because with the pocket cube, it turns out that the maximum number of moves to solve any cube is just 11, which is kind of a nice number to know. For a full 3x3 Rubik's cube, that number is, I believe, 21. And also there's more than 9 moves you have to consider there because here, right, I'm only using the 3 faces to move. And for a full Rubik's Cube, you have to consider moves on more than just 3 faces. So we can see, so this took 33 seconds to solve. There was some multi-threading here, that there's some part of the value iteration that you can do in parallel. Not all of it. So this took 33 seconds. Let's see, how long did this take? Okay, only like 15 seconds. We can see like it does take a bit longer to solve. If we have like 3 times the number of values basically that we're looking at. But we get a solution that a little bit better matches. Yeah. So actually, to move on, I'm going to actually look at the other solution, because when I did this other solution method, I was actually comparing it to this sort of 9 move metric rather than just the 3 moves. So you can look back at this. We can see, all told, what it took about, I don't know, like 30 seconds to construct the state space, and then this took like 45 seconds. and then we have the solution. Now, like once we have the solution, right, like our policy function is just this matrix. It's just a simple lookup. It's basically, it just takes like a few like nanoseconds to look up which move we should make in any given state, right? We just have to basically map a few values and then we're done. But, we did have to put in this initial work of computing the solution. The other thing we can do with this is what I'm showing here is a count of, for the entire state space, how many states are this particular distance away from a solution. And interestingly, I guess this is somewhat expected, but it doesn't actually keep blowing up until the hardest cube. We actually get like a pretty steep drop off of like the most cubes are actually 9 moves away from solution, not 11. And this may be true for the full Rubik's Cube as well, actually. I'm not sure if anyone's been able to enumerate like the full, obviously like these numbers start getting too big. But I would suspect that even for the full Rubik's Cube, that actually there are fewer cubes that are at maximum difficulty than, let's say, 3 moves less difficult than that. But, it starts out pretty as expected, right? We have like the 1 solved cube. Then there are 9 cubes that are each of those moves away. And then it starts branching up. Of course, we do get some repeated cubes. So it doesn't quite scale as bad as this 9 branching factor, right? Because obviously, 9 times 9 is 81. This is only 54. So and then of course, when we get up here, we get even like negative scaling. So yeah. Okay. So before I move on to, I was going to talk about a different idea of solving this that doesn't use concepts or techniques from reinforcement learning. But first, are there any questions about, this pocket cube and the exact solution we were able to get here?
Could you explain how you represent the action space once again?
So because this is a tabular problem, okay, so it depends on what you mean or where you mean. So this is the MDP as it is like fully defined. And the most important part of that is the transition function. So this matrix tells you, right, there's 9 rows. So this tells you if you're in state 1 and you take action 4, you end up in state, 2 million, like whatever this index is. And that's true of all of these. Now, this was filled in by going through this whole matrix and saying, okay, I'm in, state 1. First of all, like what state is that? Like what is the cube? Or sorry, no. Okay. I'm going through the states, like the actual states, which are those vectors I showed, like from 1 to 24. So I already have this mapping from states to the state index. So that tells me, where to put the value I'm going to get in this matrix. And then I just apply the rotation. So I already have this rotation function, which will take the action index, so here, like the 9 actions, let's see where that's actually listed. I think it's called, where did I define this? Oh yeah. So here, like, remember how I only had the 3 actions, and that was just like top face clockwise, right face clockwise, front face clockwise. Yeah. So here, I'm just multiplying it by 9 by just saying, okay, well, I just want to consider like any of the, doing it 1, 2, or 3 times. I'll just consider all of those at once, that I don't have to like, take action 1 3 times in a row. So here, like with this set of 9 actions here, where like these 9 actions are represented by the face and then how many times I'm rotating that face. This is like face 1 rotated once, and then this just forms 9 actions. It just turns out I do have, at the lowest level of this function, it does operate on like the move itself, where it's like, front face clockwise, but at this point in the definition, I'm just using integers because it makes things a lot easier, and it makes all the type and like when this has to do type analysis, it makes it a lot easier because it knows like regardless of whatever move you're doing, it's just this set of integers, and then at some other point it does this lookup of what move it's actually doing.
Gotcha. So, do you discriminate between clockwise and counterclockwise? I guess you don't need to if you
Yeah,
can
you
go up to
don't.
like three clockwise rotations.
Yeah, I mean, in for the full Rubik's cube. So here I'll show. Here, this is the nope. I showed that. This is what we looked at in the previous meeting. And here I have this definition of all the Rubik's cube moves. So I have the top, left, right, bottom, front, back. So there's 6 faces, and then I have clockwise, counterclockwise, and double, which is doesn't matter. It's either clockwise or counterclockwise, doing it twice. It's just a
Gotcha.
180-degree rotation, and then I have again like building up these moves. So like for the full Rubik's cube, if you use the convention that most people use, you have these 18 moves to worry about because you have right all six faces and then 3 possible moves you could make on a given face. But like that's because like if you take a full Rubik's cube and you rotate the front face and then you also rotate the back face, like that is a distinct, like you can't ignore the back face, okay?
Mm,
Because its relationship to the middle plane changes, right? But in the pocket cube, there's no middle plane. So you just have to consider like 3 faces, facing you like this.
gotcha.
Because
Yeah.
then the opposite faces don't matter. You could just imagine they stay fixed in place.
Gotcha. Like even if it, but a double clockwise or double counterclockwise, would that give you the same state again? Probably not,
What do you mean
right?
in the pocket cube or
In the
the
pocket cube.
in the pocket cube? Well, any rotation to a face, whether it's 1, 2, or 3 times, clockwise, kind of always like, um, you can always imagine that as like you can always just fix the back like 3 faces, the ones that are away from you, and you can arrive at any cube only rotating the ones facing you. And you can
Mm,
imagine that just by like if you have the pocket cube and you imagine twisting it, it's like twisting it like this. It doesn't matter if you do this or you do this. Like it's the same move
gotcha. Okay.
because you're not like they have a fixed relationship to each other. So
Okay, but that's why the reduced set of possible actions, or do you just
yeah,
consider that in the model itself that way?
yeah, no, like yeah, like that's why the action, like it, these actions, like if you look at the solution, like you could build this, you could have built this solution like here. I did it with 3. Um, you could do this with 18 moves as well. It wouldn't change the solution at all.
Gotcha.
It would just make the mapping way bigger to store, but you would still have that 11 as the at least if you do it like with the where you never have to like the point of doing it this way with the 9 moves or 9 action moves is that you never have to rotate a face more than once. Like if you rotate a face, then the next move will rotate a different face. Like you should never consider rotating the same face again. And that's important when
Gotcha.
you're looking at scrambling the cube or doing a forward search. When you're considering like how to branch the forward search, turns out so we start with like a solved cube or like wherever we are. We first have to branch 9 times for the 9 moves. But
Yeah.
then on for the next branching, we only have to branch 6 times because we don't have to branch from the face we just rotated because that is guaranteed to be redundant in the branching
Gotcha.
because
Okay.
we've already considered all possible rotations of that face from the cube in that orientation. And if we rotate that face again, we will just be copying one of the states we've already branched to.
Gotcha. Gotcha. Thank you.
Right. So because this cube problem, like the way it's formulated, right, where like the rewards are trivial, right? They're all just like -1. We could also formulate it where there's a reward of 1 for solving the cube, and all the others were 0. In that case, we'd have to formulate it as a discounted problem where here, our reward values, we have these values which are like -9, -10. In that case, we would have a value like, let's say our discount rate was 0.9. In that case, like the cube that's 1 move away from solution would have a value of 1, but then 2 moves away would have a value of 0.9, and then 0.81, right? It would be like 0.9 to that power of how far away it is. So the values would be different. They would not scale linearly with how far away they are from the solution. If we did it as so the values would be harder to interpret if we do it that way, but it's perfectly possible. Of course, because this is a tabular method, we're just storing the values individually, right? We're not approximating them. It doesn't really matter how big these values are. Like for a neural network or something, as we'll see in some other problems, it can be awkward to try to model a value function where the values range, let's say it was like 100 moves to solve or something, where the values were like -100 to 0. That could be a difficult function to model because usually when we do like nonlinear function approximation, we try to keep the values within a contained range because we want, it's the same with the parameters, with the input values. We kind of want to keep everything squashed in this range where the function approximation works. And if we just have to like arbitrarily produce a very large value, it can just make it harder for the network to converge to those values. But that's not a concern for this type of technique, right? We can just, in fact, this is the most natural way to represent the problem, and we can very easily interpret what these values are. But, this construction works for this sort of goal problem with a goal state, right? So you could think of this like a problem with a goal state is you can formulate it as a pathfinding algorithm, right? Because it's like a maze problem. It's like we have some set of states. It doesn't really matter what they are or how weird the transitions are. And then there's some place we're trying to reach. And we would like to reach the goal usually as fast as possible. And that's what this solution represents, is like the fastest possible way, right, to get from state 3 to the goal state. So therefore, we can compare this to like a pathfinding algorithm and see, how the approach compares and what the advantages might be. So, one thing, like conceptually, the easiest one to think about is probably A star. Here, this is just the Wikipedia article for it, but there's this little cartoon illustrating how this works. But the concept is very simple. Actually, if we compare this to, here, I can open this as well. So Dijkstra's algorithm is, again, this graph might look very similar to an MDP, and it kind of is, where like as the distances on the graph you can think of as like the reward values for the transition, and then we can map this problem directly and then onto like an MDP problem. So we have nodes or states, and we have distances between them, or reward values for that transition, and then there's some goal state. And this algorithm is very simple. It's basically just this exhaustive search. Here, this little cartoon will show where we just start where our starting state, and then we just start branching out. And as we branch out, we have this frontier boundary where we know, like the furthest along this particular path we've searched. And then we keep expanding the frontier boundary until one of these paths reaches the goal state. And then we know the distance to the goal, at least. And then if we save extra information along the way, then we can also know what the path was that took. But you can see that in order for this to work, like in the worst case scenario, it is an exhaustive search. Here, we managed to avoid searching these set of states because we happen to find the solution. Now, if we got lucky and found the solution like here, we could also stop. But So this will just branch out and search the whole state space until it finds the solution. Now, it turns out we can improve upon this with this A star algorithm. And what this does is it also maintains the same sort of expanded search with these frontier states. But the difference is that for each of these, these open circles basically like represent points on the boundary that are candidates for expanding the search beyond that point. And if we look at a point on the boundary, we know, first of all, we know the distance we've traveled so far to get to this point. So for each of these, we know like how far we've gone so far. Then we need one more piece of information to use A star. And that is some heuristic, which is this H of n. And now this heuristic has to be a lower bound on the distance to the goal. So it has to be strictly an underestimate of how long it will take to reach the goal. So basically, if we take the distance we've traveled so far and add to it the heuristic, it tells us the best possible value that we could get from pursuing that node. Like if we find a solution from this node, like the distance along that solution will be no better than this value. Now, the point of this heuristic is to look right at all of these blue squares or these blue circles and to rank them by that heuristic. By the distance traveled so far plus the heuristic. And then we selectively only expand the one that is the most promising based on that. So what it does is that we don't like we only go to a higher depth in the search along that path where the heuristic is the best. And the good news is that if we happen to find the goal state while we're doing this, while we're pursuing that path of the thing with the lowest heuristic value, then we can throw away everything else because that is guaranteed to be the shortest path. So even though like we haven't checked a lot of the other paths, we already know, like we have a guarantee that the other candidate paths that we haven't checked yet are guaranteed to be worse than the solution path that we found. Now, there is this slight variation of this called this iterative deepening or IDA star. The main difference between this is that here we maintain this all of these like candidate states and the paths to them. We maintain that the whole time. For this version of it, the idea is the same, except we end up like repeating the search. So we end up searching to a given depth. Now the depth is based on that heuristic. And if we don't find a solution within that depth, then we look like kind of like this one. We look at all the candidates we have so far. We look at the value, like the lowest value, which right is going to like exceed that depth threshold that we set. And this value again is like the distance so far plus the heuristic. And then we relax the constraint on the depth, and then we do the search again. But it will find the same solution as the other one. It's just that it doesn't end up having to store as much information, but its performance might be worse than this. But like conceptually, this one is easier to think about because we're just always maintaining all the information of the paths that we searched so far. So, right, I mean, using this method is like way better than doing like a truly exhaustive search, right? Because like in this way, we're able to throw away a lot of information that like, paths we don't need to pursue. The problem is like we actually need this heuristic. Now, for a distance problem, like a problem like on a map, where like we actually have a 2D map, we can just use the actual distance to the goal, like the Euclidean distance, right? By taking like the hypotenuse or this just straight line path to the goal. And then if there's no obstacle, that will be a lower bound. If there is an obstacle, right, the true path will be longer than that. But right, that path, just by definition, by the mathematical definition of it, is guaranteed to be a lower bound or the shortest possible path that it could be if there were no obstacles. Now the question is like, let's say we want to apply this sort of pathfinding algorithm to the cube, to the pocket cube, or to the Rubik's cube. In order to apply it, we would need to have some heuristic, right? Like analogous to this distance. So we can come up with, I mean, there's different ways you could come up with a heuristic. Again, like in order for the heuristic to count, it has to have this property. Let's see. Yeah, this admissible property, right? For it to be admissible, it means that it never overestimates the cost of reaching the goal, right? And that is true for just the straight line distance. So if we go back to the cube, like the pocket cube, or we think about here, I'll go back to how like here, like we're representing the cube like this with these indices. And remember, like we have these, sets of moves. Like in this case, our graph is pretty simple in terms of what the weights are. Like the weights are just like one for every step. Like every move is just, a distance of one. Like we're adding a distance of one for every move that we make. So given that distance of one, so our heuristic should be, a lower bound on how many moves it would take to solve the cube from the current state that we have. So I don't know. Does anyone have any idea of like a possible heuristic that we could use to this and to the, how the rotations work? If we want to apply some kind of pathfinding. Again, if we have no heuristic, we're just doing that, exhaustive search, basically.
The only primitive idea that I had was basically a count of a face if, two elements, have the same color in a particular face, then that heuristic would be better than, if all the colors mismatch or something, and then the same for 3 and 4. But that doesn't seem like a very good heuristic.
Mm-hmm. Okay, yeah. So we have sort of how many faces are out of place is like some idea. I mean, that should somehow be a part of the heuristic. Right, probably. Let me see, what do I have? Okay, yeah. So yeah, we can count how many cubes are misplaced, or sorry, how many facelets are misplaced, right? So this is like, what this does is it takes our cube, which again is just this list of, integers, and it checks how many of them don't match the solved cube. Okay, so this will be some, value from, 1 or like from 0 to 24, right? But then we do have to turn this into a admissible heuristic, and for it to be admissible, it has to be a lower bound on the number of moves to solution. And obviously, if, like, let's say that all of the facelets were misplaced, this would be 24. And, obviously 24 is not a lower bound because we already know that 11 moves is the most we would need to solve the cube. So but I mean, but this should be a part of the heuristic. We could also use a value of 1, right? Because we know that every unsolved cube is, right, like it can't be less than 1 move away from being solved. That is a really bad heuristic, and that would effectively just be doing exhaustive search because, right, like our lower bound is extremely, like it's a ridiculous too low of a bound. So it doesn't really give us any information. No other
I'm
idea of how to use
wondering,
this?
I'm wondering if there's any merit to also considering the number of moves you make and trying to reduce the number of moves therein, by incorporating it into the heuristic itself. Like
I'm
one
sorry, wait,
over the
what do you mean exactly? How?
um like if you wanted to overemphasize that you wanted to get to the final solved cube in the lowest number of moves possible, then something like adding like one over the step number or something like that be part of the heuristic. Try and reduce the
One
number of new moves you make.
one over the, what do you mean by the step number? You mean like the number
So
of moves
in
we've taken already?
yeah, basically.
Okay, but that is already, remember, when we have this search algorithm, right? We're keeping track of how many moves we've made so far. And then the heuristic is a lower bound on how many more we need to make. So this part, the cost to the current node is already
Oh,
included in the algorithm. Like, yes, like
gotcha.
this, like we're not so stupid as to ignore the cost incurred so far.
Right,
This is
right.
just to estimate, right, from the current node to the goal. Of course, like it could be zero, right? I mean, we know zero is a lower bound, right? Nothing's going to be less than zero in terms of the number of moves. But, that doesn't really help much. We could try it with zero though and see. This problem is small enough that we don't actually like need to have a good heuristic. But it always helps to have a better heuristic.
Another one is probably distances but of the facelets of the same color, like an average distance of each of the facelets of the same color where you traverse the different faces.
Yeah, I mean that gets a little complicated because if we rotate different faces, like we can't consider them all independently because the facelets will end up getting affected by. I mean, once you start thinking about it, if you start coming up with a too complicated of a heuristic, you realize like now you're just actually sort of hand solving the cube by thinking about how everything interacts. But here, I'll say though, there is obviously like the worst heuristic we could use is like 1 or 0. Gives us like no information. I have a heuristic built in here, which is pretty bad. It's not as bad as 0, but it is an almost worthless heuristic. But even just a little bit of help, it actually helps quite a bit. So here, this is the heuristic. It is the misplaced cubes divided by 12, and then the ceiling of that, rounding up. So does it make any sense to anyone why this is an admissible heuristic?
Yeah, the closer you are, the less number of misplaced
Well,
facelets there would
sure.
be technically.
Well, yeah, but of course, I mean, so why not just use this then?
Oh, by 12, so you want the heuristic and the cost function to be in the same um range of values, basically.
Well, no, it's not. So here, right, we're not actually computing. Well, okay. So the problem with using this is that this is not an admissible heuristic, right? Like if the cube is maximally scrambled, all 24 facelets could be misplaced, right? So this would have a value of 24. Now we know that 24 is not a lower bound on the number of moves needed to solve. I mean, we already know that because we solved it already, and we know that the worst number of moves is 11. But I'm just telling you, like, so we do know that this, in fact, cannot be a lower bound because the value is just too high. So here I am dividing it by 12, which is lower it, but this has to guarantee that it's a lower bound, like whatever I'm doing here. I can't just like divide it, be like, I divided it by enough, you know, I made the value small enough, it should be fine. Like you actually have to know this to be the case.
Gotcha. But this is probably not, I mean, in a general case, you would probably have to do trial and error, I'm assuming, for different problems where you don't know that.
Oh yeah, sure. Oh yeah. Well, no, I just said that I know this is wrong. I mean, I happen to know this is wrong because I know the solution. But
Right.
I also know this is wrong because nothing about this calculation takes into account what the moves do. Like our heuristic has to be like a number of moves, and counting the number of misplaced doesn't really have any relationship directly with the number of moves to solve.
I see.
However, doing this does make that true. And the reason is because actually, if we look at this like a full Rubik's Cube, so if I rotate a face of the cube, I change the position of some of the facelets, right? So I change the position of all the ones on the face I'm rotating. And I also change the position of all the ones around here. Now on a pocket cube, right, there's only 1, 2, 3, 4, and then 5, 6, 7, 8, 9. It turns out that there's 12 facelets whose position is affected by a rotation. So let's say that I have, 12 facelets that are out of position. And they happen to be in the perfect place where a single rotation would fix them. Then this value would be 1, which would indicate there is 1 move. Now, if any one of those out of position facelets are in a different place, then 1 rotation will not solve the cube. It will take more than that. But it doesn't matter because this just has to be a lower bound. So this is just saying, like, if all of your misplaced things were just in the perfect spot and they didn't interact with each other, then this would tell you, and obviously this is a really, really bad lower bound, because let's say all 24 were misplaced. Then that divided by, this is 2, right? 24 divided by 12. We know that it takes more than 2 moves to solve the cube. So, right, way more than 2. So this is a very bad heuristic. However, it is admissible, which is what we care about. Like, at least it is a lower bound. And actually,
Gotcha.
wait, 24. Yeah. So we can see that. Okay. So anyway, this set of functions here end up doing this IDA star algorithm where it's basically like A star, but it has a little bit better memory properties. Okay, it operates on this. And now to do this, again, I'm not actually using the set of states that I built up, because as part of IDA star, like you see here, right, like we're going to be checking all these states and building them out like as we go. Okay, so with this technique, there's like no pre-processing that has to be done. Like the only pre-processing here is maybe like the lookup of moves, or how those things I already calculated about how a move transforms the indices. But that's it. So this is now showing, if I pick a random state now, this is running this, and what it does is it goes through and first it looks for, it does an exhaustive search of everything that's 2 moves deep, because that's the starting threshold in this case, right? And we know that we can't find a solution within 2. So then it makes the threshold higher by what that value is, right? This F value of the best path that it's found so far. And then it redoes the search with 3 and then 4, and then here it happens to find a solution at a depth of 10. And it had to search. Oh yeah, and this is actually very, okay. So we know, right? We actually know that the number of states in this problem is only what, 3.67 million or so. look, for this particular state, it actually searched more states than exist in the problem. And that's because this algorithm doesn't understand the relationship between the states. So as it's branching out, it can arrive back at the same state again that it already has, right? That's like part of a different search path. That issue is not true of like this type of problem. Right? Like the way this algorithm works, it's never going to loop back on a state the way this branching works. However, the Rubik's Cube problem is not as simple as that, and it can end up repeating states. But if I run this a few more times, we can see like here it only searched like 1 million states, and depending on what state it's at, here it did 9. We can actually look. Remember from the data I showed earlier from the reinforcement learning solution, we know that the most common state is 9 moves away from solution. And there are 1.88 million of those. So if we run this algorithm, we should most often see 9 come up, because if we just sample a random state, and we could see, okay, like we got a value of 9, but as we do it now to do 9, so we know 9 is the most common, and this seems to have taken about 200 milliseconds to do 9. Some of them will, this is only like 400 like milliseconds. It really depends. Here, if we look at this benchmark result, this is showing a histogram of a few different samples. It didn't collect that many samples doing this. But we can see that there's a range of values. I mean, we can kind of ignore this extreme end of the range. The mean value is about, something like the median's like 376 or milliseconds, 500 milliseconds. So we're in this range of some, hundreds of milliseconds. And, if we improve the heuristic, we might be able to get this down to something maybe even 10 times better. Like maybe it's only like 30 milliseconds or something to do this solution. Okay, so now but we didn't have to do any work ahead of time. We didn't have to construct stateless. Like this algorithm as it's running is actually constructing the state list. Like here it did here's the 1.2 second one, right? So this took 10 moves, and this had to search a very inefficient 5.9 million states. Very bad, right? Like this is not like we know this has a lot to be desired for, but most of the time we don't have to wait that long. Most of the time we get solutions like this where it's only a few hundred milliseconds. Now we know that there's 300 and whatever, how many million states. So if we look at this number of so here, like this should be the number of hours it would take to solve all of the cubes. Like if we just said, okay, we want to just come up with the optimal solution for all the cubes, this is how long it would take. It's like every time we run this, we do this all from scratch. So it's like 372 hours. And of course, if the problem's more complicated, it gets worse than this. So, right, the advantage of this method is that we don't have to construct anything in advance, and we don't really need that much machinery around reinforcement learning and all these techniques. I mean, this is really not very much code to do this sort of. In fact, these two functions could be like mostly condensed into one thing. So we're really only looking at like 20 or 30 lines of code to do this whole thing. I mean, we do have to like have the move function that does the transformation of cube indices. And for calculating a single solution, right, this is pretty fast. Like this is way faster than this whole process, right, of constructing, right, the state space and then running, like we have like 20 seconds here, and then another 10 seconds, and then maybe another 15 seconds. So we're talking about like a minute of time needed to get this to a point where we can get this exact solution. If you think about it, like if you compare like 1 minute, right, to like 300 hours, like assuming you wanted the ability to quickly look up a solution to every possible situation in this, like this is obviously a superior method, but it requires all this amount of pre-processing. And there are other techniques in pathfinding that involve some amount of pre-processing the graph, like, right, like these algorithms are designed specifically for these graph problems. And what we do with the RL solution is we're effectively just pre-processing the whole graph in a way where we can instantly look up the optimal solution anywhere. And because this graph just has these distances between the nodes, this is very easy to turn into an RL problem. However, we know that there are many problems in RL that we can't convert into a pathfinding algorithm, right? Even though we do have this graph structure, this can handle more than one goal state, but like this algorithm, it can actually, I mean, if you start having goal states be different values, like reaching one goal means something very different than reaching another, then this starts getting really messy. Like if you have different goal states, you're just trying to find the shortest path to any goal state, then this is fine. And that would be like, right, like the problem I showed here, or if I go up, like here, right, I have like a second goal state, but I could change the reward value of this goal state, and then it's not as simple as just, well, how fast is it to reach this? It gets more complicated. And then if I start making this stochastic, then it gets more complicated. It confuses that graph search even more, because now our transitions are not as simple as just, going to a new node. We have here, if I like turn this on, this problem, this happens to be a problem from the textbook where we had this grid world, and there was this option of having like win values that blow the agent up. So if you try to move right, you end up getting pushed to some range of values above you. And in that case, it changes the solution. Here we can see what it ends up looking like. Yeah, so here, like with these stochastic win values, you get a totally different looking type of solution where you end up having to sort of loop around the goal state and get back to it. It's just a function of how these win values work. And then here we can see that based on the wind, yeah, and then it also affects in some complicated way how desirable it is to go to the second goal state instead of the first one. So anyway, that the point of this was just to look at this sort of time, like amount of work comparison between a pathfinding algorithm and a value iteration solution. But the point of the RL is that you have all this pre-processing that you do, a significant amount of it. But the advantage is it gives you like a single global solution that then you never have to go back to. And we can see, it only took like a minute to do the whole thing. So even if we change the problem, let's say we could make it stochastic, we could add weird constraints, like so that when you try to rotate the cube, it actually, there's some probability of a different face, rotating instead. And then we could also, in about a minute, come up with a solution to that. And if we add too many weird constraints, we may not be able to use a pathfinding algorithm at all, because it won't like fit into that framework. Of course, I'm sure that there are plenty of problems that also won't fit in the RL framework either. But if it can, and you do need a global solution, it is a pretty efficient way to get a global solution, especially if your problem is deterministic, like this problem is. Now, the caveat is that we had to have this all fit into memory. And of course, with the full Rubik's Cube, I had already showed this, that you can make a tabular solution if you restrict the depth that you go, like in how far away you are from the solution. So here I did it building an MDP where it went up to 6 moves away from a solved state, where here, of course, each move, the branching factor is worse. It's like 18 instead of 9. And here, let's see, I don't quite remember how many states are there. Okay, so here there's already 8.2 million states. And I could do this with 7. It gets, up to more like 80 million states. And then it's still pretty reasonable to fit into memory, maybe even go up to 8. Like the problem is, even though it might take a few minutes or more to build the state list, but then the solution itself is going to take a little bit longer. Actually here, let's see, how long did this? Oh yeah, so here this solution, yeah. So to do this 8 million, 6-move from solution, restricted problem. It took 53 seconds to solve this, right where we get. Of course, I know that 6 is the most moves away from solution because that's how I constructed the problem. But going further than this is a problem for the Rubik's Cube. So clearly, we cannot treat this as a tabular problem. Not because the state space is infinite or like continuous, like it is for some problems, where a state may be the position of something on a grid, and the position could just be a real number. Then we have an infinite state space. In this case, it's not infinite, but it's way too large to handle. Like we still have discrete states, but we have to have some other way of dealing with it. And that's where function approximation comes in, which, actually here, let me open up this thing again. So yeah, those are the tabular methods. I didn't talk at all about the estimation methods. These are methods where you don't have all the probability information, but you still have a tabular problem. So the state space is still finite. And in that case, we take a very similar approach, but we have to sample transitions from the environment. We have some way of collecting samples. We generally will have a policy that we're following with some amount of randomness in it so that we visit a lot of states. But we want the policy to keep us sort of in the range of states that are visited with an optimal solution. And then we just average data, right, using the definition. We can do it a few different ways, but the easiest way to do it is to use the definition of the value function, right? The expected value of G. If we collect data from the environment, like trajectories, we can just collect unbiased samples of G. And then we average those together to get an estimate of the value function. And then once we have an estimate of the value function, we just do policy improvement. Instead of doing policy improvement on an exact solution, though, we're doing it on an estimated solution. And then, but the concept is exactly the same other than that. It's just that, we have to have a learning rate. We have to, decay it over time if we want to guarantee convergence, and we may need to collect a lot of samples. But the whole idea of collecting this, and of course, in this case, we have to collect the state action value function, because if we're doing this estimation in a tabular problem, it means that we don't have the probability information about the problem. We can only sample from it. If we had the probability information, we wouldn't even bother with this. We would just do an exact solution method. But then for like the full Rubik's Cube, clearly we can't treat it as a tabular problem. And that's where we get into these approximation methods, which I did add here in this outline, but it is an entirely different topic, and it involves gradients and approximation functions. And I wanted to get into it. Perhaps we could think about next time whether we want to look at this in more detail with approximation or move on to something else. But since we have the exact solution for the pocket cube, we can look at the different ways of using approximation and see how successful they are. And because of how I represented the cube, right, with this vector, we can sort of transform this into a binary feature vector where I just create like a one-hot encoding for all of the integers and stack them together. And that is one way of constructing a feature vector that could be used for function approximation. In this case, the vector would have a length of 24 times 24, which is like 600 and something, I think, or I don't know, 576. So it turns out, and then we could think about using either linear or nonlinear approximation. This is obviously a very sparse feature vector. Luckily, it doesn't really matter how sparse it is, because we can actually use a sparse representation of the feature vector and still do not worry about all the zeros. All this really does is give us more parameters to work with in the case of linear approximation, right? But what I was going to do maybe next time if people are interested is look at the different ways of using approximation on the pocket cube and see, because we already know what the solution is, we can see how successful they are at solving it, and like, how many parameters do we need, what kind of architecture do we need to come up with a solution. But this is showing one example of using linear approximation on the pocket cube, constructing it as a problem, not a tabular problem, but one where we don't actually have the list of states. We just know what the states look like, and we know how to transform between them with an action. And what this is showing here is if we run this for some, this is already, it's actually quite fast for this linear function to converge. Also, because it's a linear function and the way I'm running this, you don't have to play around with parameters too much. Like it has very good convergence properties compared to the nonlinear function. And unfortunately, because right here we only have the 576 parameters, which are that's the length of the feature vector that we made with this pocket cube. We can see this number of parameters. If we do this and we train it and do, let it run until, as well converged as we can get it, we do get some success here, but we only really reliably solve a cube that's been scrambled 3 times. And if we go all the way up to 11, we don't succeed at all, and we start getting very bad performance even just at 5. So clearly, linear approximation is not good enough for this, which was probably obvious already. And then the question is, if we do nonlinear approximation, how difficult is it to actually learn a solution to this? We don't need to use any approximation, right? Because I already have an exact solution. But let's say we wanted to apply these techniques to something like the full Rubik's Cube, where we can't get an exact solution. The advantage of looking at how these approximation methods work on this problem is like we can sort of see what we're getting into. Like if we try to do this with a full Rubik's Cube, how difficult is it going to be? How long will it take to train? How large? How many parameters do we need? And that was one of my goals of looking at this at a variety of approximation methods for the pocket cube. But we can see I also tried this. So here's an example for training this. So this is now, I've tried a few different things, but this is just showing like a very simple, like fully connected neural network. I have different versions of it. Let's say I made like a really small one, with only 2 hidden layers. And we can see with just this nonlinear approximation, just a 2x2 network, how this did. So this already is quite a bit better than the linear solution, right? This was like 63 and then 26, right? And this is already like almost 77% and 32%. And then if we make the network bigger, like what did I show? Like this, 64, 4 hidden layers of 64 each. Now we're starting to get, exact solutions here. And then, if I kept it, so anyway, you have to pursue this longer to see how large does the network need to be and how much training time do you need in order to like get this 100% all the way down to 11. And that I am not yet sure about. The other thing I'm showing here is this network has 49,000 parameters, and we know there's only 3.67 million states. So, it's only 1.4% of the state space is covered by the parameters. We already know, obviously, if this network had 4 million parameters, it could solve this, right? Because we would have as many parameters as we have states. And we know that, there's already, it's not surprising that could solve this, because we could just store the correct value for that in each parameter. We probably need more than that practically to memorize the solution. But, that's not very interesting because we already have the value iteration solution. Now, it turns out like this algorithm, like the algorithm needed to solve the cube to approximate the value function may be very complex, and to actually construct it with a neural network it may need 1 billion parameters, even though clearly that is a waste of time for a network this small. But we know that the algorithm to solve a Rubik's Cube is at least as complicated and more complicated than what's needed to solve the pocket cube. So there's a factor here where like it's possible this may not tell us, like, if we saw with only 1% of the states covered by parameters, if this was already able to learn a solution, then we would know that there's a good amount of generalization happening. And that would be promising. But this doesn't mean that it's not generalizing. It may just mean that the complexity of the function may exceed this, even though like there aren't that many states in the problem. So you'd have to pursue this further with larger networks, more parameters to see at what point do you get this. Also, these algorithms all have one or more parameters to them. They all have a learning rate, but there's more than just learning rate. There's plenty of other things you could adjust. And it's always a question of, you have to train for more steps. Are you training with bad parameters? And then, it just makes it's one of the reasons why the exact solution methods are so nice, because you get an exact solution, but you don't have to tweak anything about the algorithm. Like, it's just going to work. And whenever you get into these, especially with nonlinear approximation, there's a lot of parameters where if they're not set quite right, you get really bad convergence. And if you already know, like a lot of papers even written that show like we trained a network and it did this, and they might show a final result, but you really have no idea how much tinkering there was with the parameters of the algorithm to get it. I mean, hopefully they shared everything about the process, but you could have just casually tried a bunch of stuff. And then by the time you're pursuing your experiment, you already have a pretty good idea of what, parameters you need. So, you can also do things like parameter studies, which I did some of in here, but, parameter studies are very expensive because you have to repeat training over a large number of settings. Actually, I'm not sure if I have a parameter study in this notebook. Maybe not. Well, I have it in other places. Like here's an example. You do these parameter studies where you try to look at a training algorithm and see its performance, and then hopefully you can train it in a parameter study over a shorter number of steps, and the information you get is still useful for training it over a longer number of steps, but that's not guaranteed either. So the point is, the more parameters you have, a technique could be more powerful, but the more parameters you have, it is like more things that can go wrong if those parameters are set incorrectly. Yeah. So I think, yeah, I'll stop there. So yeah, basically spend most of the time comparing the exact solution method with search methods, but for a lot of hard problems, we do need to be in this realm of approximation methods. And of course, if you look at the videos on YouTube, right, the entire chapter, the entirety of part 2 of the book and all the videos associated with that are all about approximation methods and using them. I have some more examples that are not exactly the way they are in the book, but a little more of a thorough comparison of different versions of approximation on some of the toy problems. And then, of course, also trying to see how they would apply to both the pocket cube and the Rubik's Cube. So that is one option for what we do next time. The other option would be to look at more of the book or the stuff in part 3 of the book, or just an entirely new topic or case study. So first of all, does anyone have any questions about just what we talked about today, or any ideas? And then if not, also, does anyone have a preference or idea about which topic to do next time? But, I'm basically done. So anything anyone wants to say about either of those things, feel free to say that now.
I think it would be interesting to look at, how you would, go about I know, like deciding the size of the neural network you would use to approximate the do function approximation, like approximating your value function. A lot of it is a lot of it you'll have to do like trial and error, or you'd have to do like a full hyperparameter tuning study on that, or at least have an idea of the state space and action space of your system. Um, Maybe like a just a short discussion on how you would go about with that initial guess on a set of no on the number of hidden layers, or the the number of parameters on the model generally. I think that'd be useful.
Mhm. Okay. I mean, there is this whole like I didn't do any kind of overview of how the approximation methods work in terms of the gradients, but if I did that for a future meeting, I would probably first do sort of an overview of how the approximation methods work, and then yeah, I mean, try to organize how to sort of look at all of the options for a few different example problems and show, yeah, like parameter studies, how successful they are in that sort of approach. I mean, I can also show more information about how, like this, all these notebooks, by the way, are all like, these are like the chapter overview notebooks that have all the notes, but the code in them, not all of the code, some of this code is just particular to the notebook itself, like to do a demonstration. But a lot of the code in it is actually like the algorithm implementation. So here, like this code is actually defining like how this like one approximation algorithm called reinforce is written, like in different variants of it. So I didn't go over any of that. Some of that has gone over in the previous videos, but like this notebook, which I was showing for some of this stuff, like that's what I'm like. If you clone this repository, and there's like instructions on that the thing, but if you clone this this sort of non-tabular RL package, which is contained within this repository, the code it's using for all these things, like for the value iteration that I used to solve the pocket cube, is all that code is contained like within these notebooks. So if you go and look at them at the notes and you get to the part where it's defining all this stuff, like yeah, like these actually are the algorithms, the way they're implemented, solve the problems. And then for the tabular methods, there is just this single notebook here, which has all of the implementation for the tabular methods. Yeah, the approximation methods are actually split between these 5 notebooks.
That's pretty cool. Thanks.
Yeah, so I don't know, but it depends on what people are interested in. So does anyone else have a preference or idea of what they would find most useful for a future meeting? I think I was gonna maybe default to just spending more time on the sort of dedicating more time to the approximation methods, kind of like I dedicated most of the time to the exact solution methods, and things that are comparable to them. Okay, well, thanks for coming, everyone. Oh wait, the question, I mean, translate some of the methods into code. Okay, well, if you want to see the code, like here, yeah, I mean, this obviously has some basically just math, but if you look at any of these notebooks, which are all, they're actually the meeting description itself will have a link to the repository. And there's also like PDF, or not PDF, but HTML versions of these notebooks that you can't interact with them, but they're right. You can see all the code at least. Those will have, like, if you look at these notebooks and see here, like all of these this code, like these are the code implementations for the algorithms that are described above it in the book. Like here, there's right this discussion of the math of how to do these semi-gradient methods, and then this is like the implementation of that. So yeah, you look at it. If you look at the videos that went over like these chapters 9 through 13, I go over some of that. The purpose of the meetings was more to explain like the math and the theory behind it, and show some of the results. So there is some discussion of the code and how it's written, but that isn't like a main focus. But yeah, if people are interested in more like how I approached writing the code, then we could also do a meeting of like looking in more detail at how the code is organized. But yeah, depends on if people are interested in that.
Another thing probably would be like GPU usage and how you would, what libraries you would use and how you would incorporate the appropriate libraries for that.
Yeah. I mean, this is probably so all this. So basically, all of the RL stuff in here is pretty much is like written from scratch. The one exception is for the approximation methods. I mean, for the linear methods, that's also from scratch because linear methods are very easy. For the nonlinear methods, I am using this. There's this other package you can see here, it being initialized, which is just doing like a gradient check. This is also, it is like my package for the neural network stuff, and it does have a GPU functionality in it. It's like a very simple neural network package. I wrote it mostly to just only handle fully connected networks without a lot of other bells and whistles. So it's just like, it's very fast for doing very simple things like that. Yeah, the GPU issue is interesting. I haven't, even though this has like GPU capability in it, by default, the RL algorithms, where they're written now, don't use GPUs. The problem is if you're doing certain methods that accumulate data from episodes and then do training, and there's like hybrid methods that combine a lot of techniques. And for those, you can assemble a big chunk of training data and train on it and use a GPU for that. Most traditional RL methods will look at like single step transitions and try to update the parameters after individual steps, which like it sounds inefficient, but the advantage is that your data quality is way better because like the policy is actually changing as well along those steps. And the performance is worse because you're just handling one step at a time, but the convergence could also be better. For doing that type of algorithm where you're just like looking at a single state and then, calculating gradients for it, I haven't done the benchmarking yet to see if it's actually worth using a GPU for that, because like the problem is, even if your network is really big, the actual input data is just like a single example, and usually the GPUs would excel when you have a big stack of training data that you're going through. So I don't know, I haven't actually tried it. It's possible that if the network is big enough, even a single example would be faster on a GPU. And then there's other like hybrid method cases where it would be better, but it would be a different algorithm that would involve like sort of taking breaks and assembling data together and then training on it. And of course, usually when you're doing RL, you usually don't want to ever repeat training on the same data, because like if you're generating like a batch of data, you should always just generate like a new batch, because right, you never want to even think about risking overfitting on a particular batch. And right, like data is not a problem. You can always generate more data using the environment, unless you're talking about a case where you don't have access to the environment, which is a separate problem that I'm not going to talk about. So yeah, it would be interesting to see. I was thinking of maybe adding some GPU functionality and then testing the conditions when it would actually be worthwhile to use. But I don't know.
Gotcha.
I should probably just add something in it where you like initialize the algorithm and it does like a couple of tests and then decides which to use. Like, because it could just test on your computer, like, okay, like the GPU actually was slower in this thing you're trying to do. So it's not worth using. But I don't
Yeah,
know.
that'd be
Yeah.
interesting. Yeah.
There actually is, yeah. There is another case, another variant of yeah, it's a little, but in the weeds because we didn't really talk about the approximation methods, but there is a version of the approximation methods where there is one step where you compute like a bunch of action values. And if you have a lot of actions in your problem, like we looked at problems where there was like 9 actions, 18 actions. If you have like, you could have a problem with like 1,000 actions or something. And in that case, and you want to look at the value estimate for all of those different transitions. And if the problem's deterministic, that effectively creates a batch that you need to just process and get the output of. And that may be one area where using the GPU would actually make sense, because you could just, like, if the batch is big enough, you could, load it up, transfer it to the GPU, calculate the values, and then use those. And that would be like the slowest part of that algorithm too, is doing that that value
Transfer.
calculation.
Oh, I see.
Well, no, is it's in an algorithm where there's one step where you need to calculate like a target value, and that target value happens to be involve like a lot of different states that you transition into. And in that case, you would
I
want to sort of
see.
like assemble all those states together and process them as one batch, because otherwise you're doing it, one at a time. So that's
Gotcha.
definitely
Yeah,
a
yeah.
place where the GPU would help. What I really don't know is whether the GPU is ever worthwhile if you're just dealing with single examples.
I see.
I don't know. It's possible. If you have a transformer model, it's a little different, because in a transformer model, a single example is effectively like a batch anyway, because you have like a stack of, of token like
Yeah.
embeddings. So yeah, that is yeah, but that's a different architecture. So that's another possibility. But yeah, there's things to check. But yeah, right now I was just trying to sort of organize the code as it is before I start adding more stuff like that.
Makes sense. Thanks.
But yeah, it is possible, especially it may, like, some of these things like with the Rubik's Cube may be impossible without GPU acceleration, especially like if the network is too large. So yeah, it's worth looking at for certain cases. So okay, yeah, thanks for coming, everyone. Yeah, so hopefully, yeah, we'll decide. I guess next time we'll probably pursue the whole looking in more detail at the approximation methods. But if anyone has a particular case study they are interested in, please let me know either. I mean, you could let me know either on Discord, on GitHub, or you could even leave a comment on YouTube or something after this is uploaded, because yeah, it would be good to have more, more ideas for other case studies. Granted, like, it has to be something specific. Like, it can't just be like, I want to know how RL can be used to, like, do like financial engineering or something, because it's like too broad of an idea. But yeah, if you have a specific case study that you think is an interesting problem that would lend itself to this, please let me know.